días a todos. Hoy tenemos una edición especial de los seminarios Fronteras con un invitado de Estados Unidos, el profesor Martin CRIMP de Michigan State University. Él está aquí invitado por los servicios de innovación educativa y está dando clase en la universidad. Lo que pasa es que, bueno, además le hemos pedido que nos diera una conferencia de investigación. Él es un experto reconocido en análisis de fallo y en fractografía y también ha trabajado muchísimo en microscopía de metales, que para nosotros es un tema vital, y le hemos pedido que nos hable un poco de eso, en especial de Electron channeling. Martin, welcome to the Material Science Department. Thank you for coming. Thank you for this conference, and please, it is your turn.
My turn, then you've got a couple of other slides?
Yeah.
Okay, there we go.
Sorry.
That's okay.
This is
okay.
Okay, it's for you.
Okay, well, first of all, I want to thank you very much for hosting me here. I'm really pleased to be able to participate in this exchange program. We've had some of your students come work with us, and I guess one of our students is over here right now, and I hope this can be a lasting relationship with Michigan State and Applied Technicum here. I also apologize for my very poor Spanish. I've said about all the Spanish I know so far, right? So, very sorry for that, but I guess we'll just have to do that. Yesterday, I actually gave a talk over in David Morse's lab at the National Metallurgical Research Center. I don't know the exact translation, but I talked some there about anisotropic plastic behavior and damage nucleation in titanium. And today, I'm going to talk about something a little bit different. I'm going to overlap a little bit with that talk, but I'm going to talk really more about a technique and some techniques for examining plasticity that are something that I've been working on for now, about 10, 12 years or so, that allow us to do things that we've traditionally done with transmission electron microscopy, maybe do some of those sorts of studies using scanning electron microscopy, which makes things a little bit easier. And so I wanted to introduce you to those ideas. Here's a pointer. Obviously, we want to thank the people who supported this work over the years. I think, like in your country, a lot of money comes from our federal government, and so a number of different federal agencies, and some internal money from the state of Michigan through the university itself. A number of graduate students over the years who have worked on the details in this project. Some people I've collaborated with, Tom Beeler and Darren Mason. I have no idea why those fonts changed, but this may be what happens when we change my talk onto your computer. There may be some surprises as we go. Some of the stuff I'll talk about at the end with Kevin Spear and Peruz at Case Western Reserve. And then at the very end, if I have a little bit of time, I want to cover some stuff for looking at sort of mesoscale strain measurements with a new technique that we've recently developed. So I guess the question comes about, why would we want to use Sfcm for examining microscale plastic deformation versus things like TEM? Well, first of all, how many people here have ever made a TEM sample? Okay, how many people have ever enjoyed making a TEM sample? Okay. Certainly very difficult, time-consuming. I have a hard time getting students to do this. We have to make a thin foil. Sfcm really only requires us to prepare one surface. We do have to do a good job on one surface, but because there's only one surface, it's certainly less prone to artifacts. There's more things that can go wrong when you make a TM foil that may affect your final results. And we can also quite often do tests after we prepare the sample rather than prior to the sample, which gives us a chance to see if the sample is good before we do, for example, a mechanical test. That's more difficult to do with the TM foil. Also, Sfcm may be non-destructive. It may allow us to test the same area through a sequence of steps and see how the material changes during the deformation processes. Rather with TM, typically what we have to do is deform material, extract the sample, and see what it looks like. And then we're done with that sample. Also, TM has a very limited thin area, and especially if the sample preparation is difficult, it's a very limited thin area. Sfcm typically allows us to look at very large areas, and this makes it much more useful to try to assess a broader scale nature of the material of interest. And also, if we use bulk samples, we can typically do in-situ experiments in an easier way. I have done in-situ TEM and watched how dislocations move in the TEM. It's very fascinating to do. But for example, the state of stress that you get when you do a tensile test on an or on a TM foil is very difficult to characterize. You really don't know exactly what's going on. With a bulk sample in SCM, we have a very good idea of what the bulk state of stress is, and we can relate that more directly with what's going on in the material. So hopefully we'll see some of those things as we go on. But the other hand is, SCM is not going to solve all the problems. We do have to use it in complement to TEM, and sometimes we're just stuck having to do TEM. So when I talk about these sort of techniques, some of these will be familiar to you, and I think some will be new. Electron backscatter diffraction patterns have become very common in the last 20 years. We use them very extensively. When I started doing them, it would take 30 minutes to determine one orientation. Now with fully automated systems, we can get 500 orientations a second. So you can just get extreme amounts of data very quickly using it. It's very useful for orientation determination. Has significant but not perfect applications in phase identification. What we focus on, and I'll talk a lot about today for some different reasons, are electron channeling patterns, and they've been around for a very long time. And sort of a subset of those are selected area channeling patterns. They allow us to determine the orientation perhaps more accurately or in a different orientation or configuration than you do with electron backscatter diffraction. They can also be used by for phase identification, but we're not going to be doing that. And then really the thing that is somewhat unique is this idea of electron channeling contrast imaging, the idea that we can image fine-scale defects such as dislocations and microtwins in SCM, something that a lot of people haven't thought about doing in the past. So very briefly, can we see that well enough? That's pretty dark, and I apologize. I don't know if it helps if we turn off the lights in the room. Will that hurt you? Oh, we can't do that. That's... Okay. Yeah, there are actually very few dark lines on these slides, so hopefully we'll be okay. Whoops, sorry. So the idea with electron backscatter diffraction is we have a sample tilted to a fairly large angle. We have an incident stationary electron beam. We get inelastic scattering in the sample. And those inelastically scattered electrons diffract to form Kikuchi lines that we detect on some sort of a screen. And so the idea is you have a sample, again, that's tilted. We focus the spot on a given area. We collect these on a fluorescent screen, which then is recorded with the CCD camera. And we get patterns like this, which we can then use a Huff transform to determine the orientation. And so we can do maps like this, and actually this is not accurate now. This is a few years old. This is rates up to 70 orientations per second. This is more like about 500 orientations per second if everything is now working correctly. But more what I'm going to focus on is this idea of electron channeling. With electron channeling, what we have is a situation that simply, as the electron beam orientation changes, or if the orientation electron beam remains the same, but the crystal orientation changes, the backscattered intensity is going to change. And so there's a number of different ways that can be used to give us information about our sample. If we take a typical polished polycrystalline sample and we look at it in typical backscattered mode, and if we don't have other things going on like phase contrast and things like that, grains with different orientations are going to give us different backscattered intensities. So as a result, we can see the grains quite easily. You can even see little details like the subgrain boundary along here, and there's another one there, that is indicative of this change in backscattered intensity or backscattered yield as a function of the crystal orientation. If we take a single crystal of silicon, so now the orientation remains the same, but we look at that at very low magnification. As the orientation of the beam changes as we image a sample, and that's effectively what happens in an SCM at very low magnification. We get a beam raster where the beam orientation changes. We'll get a series of lines that is indicative of the crystallography of the sample. And each one of these bands here is going to represent a set of crystallographic planes in the sample. So from this, we could determine the orientation of the sample. But in this format, this is not very useful for us because we're really limited to using this on very large single crystals. But if we rock the beam back and forth through two angles and try to rock that on a point on our sample, as we rock that beam in those two angles and we output the intensity, we can actually then get a pattern that now reflects the crystallography of the sample. And so the center of this pattern represents the unrocked beam, or the orientation of the microscope axis. And this pattern now, which we refer to as a selected area channeling pattern, this pattern here is going to represent what is the orientation of the sample relative to the optic axis of the microscope. And that becomes very valuable for us before we're done. And we typically don't use these necessarily for trying to just in general find orientations, but we want to be able to use these in the way you would use a selected area diffraction pattern in TEM in order for us to set up specific imaging conditions. And so that's quite useful for us. There are some problems with this. Just in terms of the general sense of a scanning electron microscope, what you can do with this. First of all, a lot of SEMs are incapable of doing this. They used to be offered as a fairly standard option on SEMs, but it is much less common these days because EBSD has become so widespread used. But first of all, what happens if we don't rock this beam on the surface of the sample? Let's imagine now it's rocking down here, and that's very common in a lot of microscopes. Well, certainly then as you rock the beam, it's going to sweep across the sample. And so if you cross things like grain boundaries or into different orientations, we're going to get channeling information from those different orientations. And so this means that the resolution of the technique, the spatial resolution, is really quite limited. So if we can adjust this rocking point and put it right on the sample, we can certainly get information from a smaller area, which becomes more useful for us. But there's still a problem here. And if you look at both of these and these, what we see is that actually these rocking beams don't come to a point. And the reason is, as this beam rocks back and forth, it's subject to spherical aberration in the objective lens of the SEM. I kind of have it drawn backwards, but generally what we're saying is the beams that are farther from the optic axis are more strongly focused. And a result of that, you get a disk of least confusion associated, which really defines the minimum area that you could collect information from. But if you actually adjust the strength of the objective lens as you rock the beam, you can actually get that area down much smaller by using a dynamic correction. And as a result, we can get information from a smaller area on the sample. And the smaller the area, the more useful it is for us, because it allows us to measure specific orientations in small grains, or if grains have orientation gradients in them, we can separate those out. So if we kind of make a comparison of what an EBSD pattern looks like compared to a selected area channeling pattern, here's an EBSD pattern. It actually collects a very large angular range, probably about anywhere from 45 to 60 degrees, depending on how you have the system set up. So we have these bands that now correspond to these different crystallographic planes. Where a lot of these bands come together, we get zone axes where that represent high symmetry orientations. There are some limitations. Things like superlattice information is not contained in these bands. It's there, but it's really hard to see. If we compare that to a selected area channeling pattern, here we actually collect a much smaller area. Now we can directly compare these two, but now we're collecting information from maybe 5 degrees. And so that makes it more difficult to determine exact orientations because we don't have all this broad information. On the other hand, we can see fine details. For example, these lines here are superlattice bands, which don't show up in these other two bands. This happens to be a 1-1-1 axis in titanium aluminum. And now the center of this pattern, again, corresponds to the electron beam direction during normal scanning. And that's what makes them very useful for us. Okay. So to kind of compare those a little bit more, EBSD has spatial resolution, certainly less than 1 micron. Some people will say, tens of nanometers. It really all depends on how you're defining your backscattered electron interaction volume and how that is as a function of direction in your tilted sample. It has a fairly complex interaction volume. The angular accuracy in general is not all that good. First of all, there's scatter in how the Huff transform solves the orientations. But on top of that, what happens is this is a calibrated orientation. It's done based on putting a piece of silicon in the microscope and calibrating that orientation and then hoping you get your sample oriented in the exact same manner. And if the orientation angles are off a little bit, as you put that in the, I should say, in the mounting angles, that's going to cause some problems there. There are certainly some techniques out there. For example, Angus Wilkinson at Oxford has come up with a relative orientation accuracy, which is extremely accurate, down to about 0.001 degrees. But that is really just relative to other orientations in the local area. Again, fully automated, though very fast. Fine structure is not well resolved. With selective area channeling pattern, it's about the best we can do is maybe about 5 microns. So the spatial resolution is not nearly as good. If we don't have dynamic correction, it's going to be even worse, about 100 microns, which really starts limiting this approach. But the angular accuracy relative to the optic axis is quite high. It's about 1/10 of a degree, maybe a little bit better. Only minimum automation, which my students don't like because it makes them work hard. Okay? And we do get fine structure resolved, which I'll give an example here, how that can be really very useful for us. So if we kind of look at the sorts of things we can do, I think we can imagine now if we could see contrast from different orientations in a polycrystal, we could certainly see contrast from different orientations associated with twins. As we move across a twin, when the orientation changes, we're going to get a change in that backscattered yield, which is going to reveal the twin. But we can actually do that with pretty good resolution. This is a secondary electron image of deformed TiAl, and this shows actually a twin boundary, an annealing twin boundary, and then these fine lines are actually deformation twins. And those are very, very small. You can see in some cases those are in the order of tens to maybe hundreds of nanometers across, and so they're very fine twins that we can resolve actually very easily in the SCM if we set up our imaging conditions correctly. If we want to see a dislocation, imagine this as a dislocation here. As we raster the beam across the sample, we can imagine now locally the orientation is going to change. And as a result, if we could imagine the channeling pattern that we could get near that dislocation, we can't measure that obviously, but we can measure it. We can imagine that the center of those channeling patterns will represent the local backscattered yield. And that local backscattered yield will be given to us by what is the intensity on that pattern at that given orientation. And because the pattern shifts as we move across the sample, we're going to get changes in intensity as the beam moves across that dislocation line. And as a result, again, here's a secondary electron image of very flat polished surface. But when we image it under the right channeling conditions, if we set up the orientation properly, we can actually see the dislocations in the substructure actually fairly clearly. Here's actually a deformation twin, and you can see it sort of peters out here. And so these dislocations right through here are actually the dislocations at the leading edge of that twin. So we can resolve them reasonably well. Maybe not as good as TM, but not perfect. Now this is kind of a noisy image here, but I want to show you that, funny, people look at these things and say, yeah, well, the dislocations look a little bit different than they do in TM. Well, you might expect them to, because we have a bulk sample, and we're only really looking at the dislocations that are close to the surface. And in fact, theoretical work was done in Peter Hirsch's group many, many years ago on this, and shows basically if we take the trace across a dislocation line, as you go deeper into the sample, that intensity, peak to background, is going to decrease. And as a result, we can imagine that the dislocations are going to be sharp where they exit the surface, and as they go deeper into the surface, they're going to become noisier and eventually disappear. And at first people say, well, that's sort of inconvenient, but the reality is that's a really good thing. Because if we were seeing all the dislocations through the depth of a bulk sample, we wouldn't be able to see anything. They would completely overlap and make it difficult to see. So this is a useful thing for us, but it also means that it's going to be a little bit more difficult for us to interpret the dislocations relative to how we're used to seeing them in TEM. Well, how do we do this? Well, it's a fairly straightforward situation. We use a field emission gun SEM. We use a typical backscattered electron detector pole piece mounted. On some of our microscopes, we've gone to retractable detectors because we want to be able to get it out of the way at times. What we do, and I'll discuss a little bit more, but we generally use the specimen pretty much perpendicular to the incoming electron beam. We can tilt it about plus or minus 30 degrees and still be able to use this fairly usefully. But this is a different configuration than a couple of other people use. The field emission gun, because it's a thermal gun, gives us a pretty good beam current, and that's been a big advantage to us. We have a beam divergence of about 8 milliradians. We work at typical SEM kind of working distances, and that makes our life really nice, because what we're able to do is use various deformation stages, things like that, that would be much more difficult to do if we were in a high tilt configuration, and quite frankly, impossible to do if we were doing this in a TEM. This typical backscatter detector with these working distances gives us a fairly large detector collection angle, which is very useful for us because what it does is gives us a lot more electrons on the detector, which really makes life easy. And one of the critical things for us is generally you're going to need to be able to collect these channeling patterns in order to set up the proper imaging conditions. Just going through a number of the parameters in no particular order, one of the reasons you need a field emission gun is you need a high brightness, but you need to do that in combination with a small beam convergence. And a typical thermionic, either tungsten or lab 6 gun really can't do that for you. Here's some theoretical work by David Joy about 20 years ago that shows some dislocation profiles as a function of beam divergence. You can see the peak to background decreases as the beam divergence increases, and if you get much below this, you end up getting a real flattening. You really can't image your samples well at all. The other thing worth noting on here, if you look at these sort of peak to background positions here, the widths of the dislocation lines are similar to that you'd see in bright field TEM imaging. That's about as good as we're going to do. We can't set up anything like a weak beam condition like you get in a typical TEM, because here we're really limited by the probe size in terms of our resolution, rather than some of the other things associated with weak beam microscopy. How do we set this up? Well, in many ways, this is the same thing as you would do in a TEM. In TEM, what you would do is you would go to diffraction mode, you would tilt your sample to a 2-beam condition, you'd adjust your deviation parameter by moving your Kikuchi lines relative to the positions of your diffracted beams, and then you'd switch back to imaging mode. Well, what we do here is we go to diffraction mode, we tilt to a 2-beam condition, we increase the magnification of that pattern, and we put the center of our pattern right on the edge of one of these channeling bands. And the reason we do that is this is where we get the most dramatic change in contrast between the dislocations, bending the planes in the background. And then what we do is we just switch back to typical imaging mode. So here we're rocking the beam, and then here we're just rastering the beam back and forth across the sample. So in many ways, we can envision it a lot like what we do in diffraction contrast TEM. One thing that's a little bit different, and those of you who are familiar with TEM, you realize that the dynamical theory in particular, well, actually kinematical and dynamical theory, both tell us that we want to use a deviation from the exact Bragg condition, and the dynamical theory says we have to do that with a positive deviation from the exact Bragg condition. It turns out with this, we actually want to set up our channeling condition exactly at the Bragg condition. And this shows, again, a number of theoretical profiles. And again, this was all thought about really 40 years ago by Hirsch's group. And they sort of gave it up because they didn't really have good microscopes for doing it. And so you can see that if our dimensionless deviation parameter is equal to 0, this shows the maximum peak-to-peak contrast associated with this. And so what I've shown here now are some experimental images that we've done. This is a selected area channeling pattern that effectively shows the locations of the non-tilted beam, which gives us really what the deviation parameter relative to this channeling band. And we can see when S is less than 0, the contrast is very poor. When S is equal to 0, we get strong contrast. When S is greater than 0, we maybe don't get a strong contrast, but we get a little bit sharper images. And so generally, we want to be in these kind of imaging conditions in order for us to be able to get the best image, best contrast, best resolution of our dislocations. A couple of other things. If you're familiar with TEM, you can imagine setting up diffracting conditions with a minus G condition or a plus G condition. The same sort of situation occurs. We get a reversal in contrast. We can see, for example, we go from here dark to bright. Here we go bright to dark, which really makes sense because we're saying one side of the dislocation is giving us a dominant diffraction rather than the other side of the dislocation. We can also do things like G.B contrast analysis. It's not trivial because tilting from one Bragg condition to another Bragg condition is time-consuming and not as easy as it is in TEM. You got a problem? Oh, light. Okay, yeah. Light would be fine here, okay? And again, here's an area where this is secondary electron image. These are dislocations in silicon here. And the critical thing is you can see there are changes in contrast with these different dislocations as we tilt to different channeling conditions. These are the only TEM images I'm going to show you, but there's a reason for this because I want to demonstrate the G.B cross U criteria. What these are prismatic loops in iron aluminum. The Burgers vector is 001, which is coming out of the board. And so when we look at these dislocations here, A and B, those both have the same Burgers vector. The critical thing is, depending on your G vector, when your G vector is parallel with the dislocation line, those dislocations go out of contrast. And we can see that both here with the 020 and here with the 200 reflections. When we go over and we do the same thing with the channeling conditions, we can see that in this image we get segments that are both light or dark, that are both in contrast for these 110 type reflections. But when we go to these 200 reflections, we see only one direction is visible. So again, the same criteria hold. And so that means that if we're very careful, and it's very tedious work, I'll be honest, my students don't like doing it, but we can determine things like Burgers vectors, and we can certainly determine things like line directions through trace analysis, rather than having to make a TEM foil to do those things. And again, sometimes that's a valuable thing to do. I want to take a second to talk about how we do our sort of approach versus other people. A lot of people actually do this at a fairly high tilt configuration. And the reason is your backscattered yield increases as your tilt increases. And so typically EBSD is done at large angles, and that's the reason for doing them at large angles. That, and also you can fit a camera on the side of the chamber, and you can't put a camera right on top of the pole piece of your microscope. And so that certainly is an advantage because you'll get more signal at higher tilts. But there's some disadvantages to that. First of all, if you're at high tilts, what tends to happen is your image gets squished together in one direction, and you have to focus differently as you raster across your sample. You can certainly do some corrections in a microscope to take care of some of those things, but it isn't necessarily an easy thing to do. This is the same area shown here, and this is a lot easier to understand what's going on here than it is here. But the thing that we have found more difficult is when we are collecting these selected area channeling patterns, if we do it at a high tilt, what happens is the intensity is varying as we're rocking the beam back and forth because that trajectory is changing. And so your selected area channeling patterns will come out something like this. But if you do that same sort of beam rocking to, say, 10 degrees here, we can see that we get much more even intensity, and this just makes life easier. The third thing is, if we have our sample tilted way over, it becomes much more difficult for us, for example, to use our in-situ deformation stages. They start knocking up against the pole piece of our microscope and things like that. So just working at a low tilt makes life a lot easier in a microscope. And so that's why we prefer to do it that way. And so given that, it's really quite, this technique, electron channeling contrast imaging, is really very well suited for particularly in situ experiments. Now what I'm going to go through is I'll show you some things from both in situ and ex situ experiments. But the sort of thing that we can do is we can do both in situ or ex situ 4-point bending. The advantage here with 4-point bending is we can look at the tensile surface of the sample where the maximum stress is. And that really helps us work our way through some things. We can also look at the sides of 4-point bend specimens in situ, and I'll show you some examples of this. And this is quite useful for us to get a general feel for how a crack is propagating. And finally, what we can do is we can actually do some fairly high cycle fatigue in bending too, which again allows us to look, for example, at the tensile surface in a fatigue sample. We have a stage that will go at about 500 cycles per minute on our microscope. Obviously, we have to stop it to actually image, but we can do some fatigue testing, and then we can look at it, and we do some more fatigue testing and look at it, which is a useful thing for us. So what I'd like to do is now just go through a few examples of the sorts of things that we can do with this. The first thing I want to show you is how we can look at crack tips. And this happens to be a nickel aluminum, which 20 years ago was a very exciting thing for people to look at. And we've been sort of looking at this a little bit more and more over the years. And what we've done is we deformed these with 4-point bending. And in this particular case, I won't go into a lot of details about this, but I want to show you really the capabilities of the technique. We can determine how alloy purity and thermal history are affecting the crack tip behavior and the crack propagation. The reason we're looking at this is commercial purity nickel aluminum is susceptible to strain aging and brittlement. It becomes essentially a zero fracture toughness material if it is cooled the wrong way. High purity nickel aluminum is much less susceptible to these variations in thermal history. And so what we're doing is we're taking a sample like this. The nickel aluminum still is very brittle, so we actually bond it to an aluminum substrate, really just to increase the toughness a little bit. And we take the sample and we put it in our deformation stage here, and you can see it right there, maybe, okay? And all we're doing then is we're deforming this, and we're looking at how the crack propagates out of this notch here. And so this shows you the notch, and you can see how the crack deformed here and actually branched here. Here's a secondary electron image of that crack tip. But now when we actually look at the crack tip with channeling conditions, we can see the individual dislocations out in front of the crack tip. So we can measure the extent of the plastic zone. Certainly as we get closer to the crack tip, the number of dislocations increases dramatically. That is partly the reason we get all this blooming here. Also what happens is as the beam comes very close to the edge of the sample, some more backscattered electrons leak out the side, which gives us increased intensity. But the critical thing is really what's occurring out here in terms of being able to directly measure that plastic deformation field out in front of a crack. The other thing, though, is because we have a bulk sample, instead of just looking at the crack, what we can do is we can look anywhere along that previous crack. And so we get a feel for how big the crack tip was as it propagated. Here we can see in the slow-cooled commercially pure alloy, there's just a couple of dislocations along there. And you can see that really it's a very flat fracture. In the same high purity material, slow-cooled, we can see it's a much more tortuous path. I think there's an indication of little bits of plasticity right along there. But we can also see dislocation slip bands along here. And we can see that those on this side go out to about here, which gives us a feel for how big that plastic zone was as the crack was dynamically propagating. Now there's maybe some relaxation after the load is released and everything, but what we've seen in general is the crack tips, or I should say the plastic zone, ends up being much larger when the crack actually arrests. So it runs out there, and when it slows down, we seem to get a little bit larger plastic field. The other thing that's interesting to note is how the dislocations are significantly different on either side of the crack. And we haven't characterized these fully, but certainly these dislocations are more or less end-on, so they look like points. Where these dislocations here are lying in the plane of the foil, or not foil, plane of the sample, and certainly aren't lined up in these same sorts of slip bands along here. And so I think we have a tendency when we think about crack tips to think about the dislocations being pushed out in a symmetrical way in front of the crack tip. But the reality is that doesn't need to be the case. And if you really think about it, it probably isn't expected to be the case. And so we can certainly see things like that. Okay, and then I can talk a little bit more detail about TiAl. This is just a gamma alloy. And we've spent quite a bit of time talking about deformation transfer in this alloy. And what we're trying to do is really understand the processes of what happens at a grain boundary in terms of if we have a dislocation pile up or a twin piling up at a grain boundary, how does that transfer deformation into the next grain? And are there some grain boundaries where that happens easily? Are there other grain boundaries where that is more difficult? And particularly, are there some grain boundaries that are susceptible to damaging through this process? And so, in a broad sense, we're trying to understand how texture and boundary misorientations affect the ductility and fracture process. And we're trying to experimentally measure how dislocation and twin generation occurs in these polycrystalline materials. And then quantitatively characterize the impact of this boundary misorientation on this deformation transfer. So to give you a little feel, and I don't want to go into a lot of detail, there are some people here who do know about TiAl, okay? Others of you may not be that familiar with it. It's an FCC derivative structure, but as a result of how the planes order, we have super dislocations, ordinary dislocations, super dislocations, and deformation twins. And the deformation twins are kind of unique is that they occur on the typical twinning plane in FCC, the 1-on-1 planes, but there's only one twinning direction. The other two twinning directions won't be active because they would be superlattice intrinsic stacking faults with much larger Burgers vectors. And so we can get all these things going, but one of the tricky things in here, and one thing that EBSD struggles with, is because the C on A ratio is very close here. EBSD has a hard time distinguishing between the C direction and the A direction. But this leads to a large anisotropy in the plastic behavior, so we really need to know the difference between those two. And we can do that by identifying where these superlattice bands are, which I've shown on this quadrant of a stereographic projection. So instead of having to deal with a simple stereographic triangle, which we would have to in FCC, we really have to worry about a much larger stereographic, a portion of the stereographic projection to give us all the information there. So the first thing that we did is we said, okay, let's try to map a material like this with EBSD. And what we find is we get a lot of speckling going on there. And the reason is one time it decides one direction is the A direction, and another time it decides another direction is the A direction. There's a hard time sorting that out. And so what we found is if we use selected area channeling patterns, we can now go in there, and in particular, if we focus on this zone here, we can see in one of the three 220 bands, we can see the superlattice bands. Those superlattice bands then allow us to determine exactly where our orientation is within this stereographic quadrant. Using that, then, we can take this pattern and run a little algorithm to correct these patterns to give us the true orientations. But then what we can do is not only do we know the true orientation of a particular grain, what we can do is we actually then can go back and see the large crystal rotations that are associated with the plastic deformation there. So this is something that EBSD really doesn't allow you to do. We have to supplement the EBSD with selected area channeling. Oh, okay. This is what my students do for me. I apologize for that. And I didn't know if I'd done the PDF, that wouldn't have happened on me. Okay. And so then what we want to do is really look at the same alloy, but we're going to look at the deformation behavior a little bit by looking at, first of all, this loading configuration, which gives us some hints of what's going on, and then looking at this loading condition, which is going to give us some statistical basis to make some conclusions. And so the first thing we want to do is look at some of these boundaries and see what's going on. Again, these are Sfcm images, and here we can see twins piling up into this boundary here. And we can see actually large numbers of dislocations being transferred into the next grain associated with these twin pileups. We can also see there are certainly background dislocations here and here, but we can see there's a much larger, really too large to resolve, numbers of dislocations associated with that strain transfer there. If we look at a crack tip propagating out of one of these notches here, we can see some interesting things. As the crack propagates along, in general, what happens is it propagates by cleavage. But every now and then, we get some intergranular failure. And not only that, we see places like this where the crack propagated here and suddenly jumped onto a different plane. And we've seen that in a number of different places where we go from cleavage to intergranular. And sometimes intergranular is renucleating on a different plane. Or, I'm sorry, ahead of the crack. Okay? So if I look at that crack tip in some more detail, we can see there's actually a lot of deformation going on here. We can see that there are lots of deformation twins. If we look closely here, we see kind of a rough, or what I would call mottled background, which suggests we have lots of dislocations there, and they're really difficult to resolve at this point. Because we know the true orientations of all these grains, we can now do trace analysis to identify the specific planes. And with those specific planes, we know that there's a specific twin direction. So we know all the crystallographic details of these deformation twins. We know exactly what twins they are, rather than just saying we have a twin on a given plane. And that's going to become useful for us here in just a second. What I want to do is concentrate on what's going on up in this little zone up here, which you'll see in the next slide. So this zone is right here. And what we see is we have a bunch of twins here. And right at the tip of some of these twins, we have some very small microcracks that are nucleating. And at first blush, we looked at this and said, well, the twins are running into the boundary. and that's creating a crack. But in fact, what's happening here, which I think is maybe even more interesting, these twins are actually nucleating here, and they end up terminating. You can see some here terminate as they move out from that boundary. So they nucleate here, but when these twins nucleate, they leave cracks behind, which is kind of interesting. And as we deform it a little bit more, we find that actually that boundary right there opens up into a larger crack. And so this is a mechanism where what we have is deformation is blunting the cleavage crack, but that deformation is also renucleating cracks further ahead. Okay, so we tend to think of deformation as inhibiting fracture, but deformation may also nucleate fracture. Okay? And if we do the crystallographic analysis on this, again, we know the exact nature of those twins. So we know twinning is unidirectional, and so we know we'll have a specific shear associated with a twin. And we find that these microcracks are located asymmetrically in relation to the twins. And that asymmetric nature is completely consistent with the shear that we expect from those twins as they open up. And so we're very confident that the microcracks form as a direct consequence of the twins nucleating at that boundary there. So what we've done now is, instead of looking at that side of a sample, 4-point bending, what we've done is we've gone and looked at the tensile surface of these 4-point bend specimens. And what we find is there's actually quite a few places in here where we get these sorts of cracks nucleating at these boundaries. And so this is a little bit of a complex microstructure. It's not just pure gamma. But we found that the majority of 20 boundaries we saw cracked, the majority, 15 of those, were at gamma-gamma boundaries. 3 were at alpha-2 gamma boundaries. One of them was between 2 alpha-2 particles, and one was between a couple of lamellar colonies. And so we're going to focus on these right here. Where do these boundaries crack? And really the question comes up is, why do they specific boundaries crack and other ones don't? We have twins interaction with the grain boundaries. Are there good grain boundaries and bad grain boundaries? And if we can understand what are the good grain boundaries and the bad grain boundaries, maybe we can do something in processing to eliminate the bad grain boundaries. So again, here are just some more examples of these. We can see these little tiny microcracks here, the microcracks there. And at first we looked at this in terms of a slip compatibility factor that was developed by Maria Morris a number of years ago in titanium aluminum, which really just says how well aligned are the deformation systems. What is the angle between the slip plane normals, and what is the angle between the slip directions? And it would make sense that if those are well aligned, slip transfer might be easy and you won't get deformation. And so this factor here can range between 1, which says it's fully compatible, and -1, which would be fully compatible for dislocations, but it would be anti-compatible for twinning, because twins are unidirectional and you can't shear them in either direction. Okay? A value of 0 basically says that the deformation systems are at 90 degrees to each other. Okay? And so if we look at this in detail, we find that, and do I have this on the next slide now? Okay? We find that in general that if we have a high M prime, we tend to see that's where we get evidence of transfer across boundaries. You maybe see a twin coming to a boundary and a dislocation pilot moving across, or a twin coming in and a twin propagating across. And so the factor works really quite well in terms of deformation transfer. The question is, if you get deformation transfer, do you get fracture or do you not get fracture? It's a little bit different question. And so we looked at that and we said, okay, what is the Schmid factor for a particular deformation twinning system? And what is this M prime? And this shows it for twin-twin compatibility, but we've looked at compatibility for different types of systems. And we plotted the cracked boundaries versus uncracked boundaries. And you can see that there is not a strong correlation. Okay? It says that this factor says that even if you have good deformation compatibility, that does not predict whether or not you'll get fracture at the boundaries. So what we did is we came up with a different factor based on work by Gibson and Forward, who suggests that the twinning shear in this material tends to be accommodated by dislocation motion. And we put together this factor here that takes into account a lot of things. First of all, the Schmid factor of a given twin system. In other words, how likely is it for that twin system to be active? How is the Berger's vector associated with that related to the tensile direction? because if these are parallel with each other, it means that in general you're going to have more of an opening force on that boundary. And then how well can the twin shear be associated or can be related to ordinary dislocation shear in the material? In other words, how well do these accommodate each other? So this kind of shows a model of this, where if we have cracking, we're going to have this situation. If we don't have cracking, we're going to have this situation, taking into account these various factors. So when we did that, we ended up looking at a couple of populations, a population of crack boundaries and a population of uncracked boundaries. And I was going to kick out of this because I've done TEM for 30 years. And nobody ever does statistical analysis using TEM. And why is that? Because how many people have ever made a TEM foil? Okay. But this allows us to do enough observations for us to get some relatively statistically relevant types of data. And so what we've done here is we've used this factor and we've calculated it for the cracked boundaries and the uncracked boundaries. And we looked at those populations and did a student t-test. Are you familiar with the t-test that compares two populations? And the question that it really asked, is it actually one population or is it two populations? And so based on this factor, we do this t-test and we get the probability that these are actually the same population of 0.005, which suggests that these are actually distinct populations. It doesn't mean we can necessarily predict what boundaries are going to be cracking, but we can also say if we take a collection of boundaries and we look at what their factors are, is it more likely one falls in one population or more likely it falls in the other population, which is getting us towards predictivity. The most interesting thing, though, is if we look at the individual factors associated with this, and we do the same sorts of tests, we see that the probability doesn't break out the same way. So really what it says is that the boundary cracking we're seeing here is a function of multiple variables that are involved. And I guess it shouldn't be a surprise to anyone, but it also means that whenever you go to any material, you've really got to look at a lot of the details and the crystallography and how things interact to really understand why some boundaries may fracture and why some boundaries may not fracture. It's not a simple process. Okay, so I want to show just a couple of other applications here, a little bit of work we've done in terms of device materials. 5 minutes? Okay, 5 minutes. I'm almost there. Okay, dislocation densities tend to be lower in device materials, which actually makes this technique maybe even a little bit easier to use. This is a MOCVD gallium nitride. These are threading dislocations. Again, here's a secondary electron image, extremely smooth surface, but we get lots of threading dislocations coming through. And so this gives you the ability really to map where the dislocations are quite easily. But what we want to do is see if we could apply this a little bit more broadly. And this is the stuff with Peruse and Kevin Spear at Case Western, where they brought me this chip and they said, well, they've done some thermal imaging on this, and they see these lines and they think they're dislocation. And they said, can we see if these are really dislocations? And I said, well, we can see if we have lines that image like dislocations, and do they look that way? And at first blush, we thought this would be quite a challenge because it's a little bit hard to get an orientation from something like this, or so we thought. But the reality is that this is a heteroepitaxial situation, and this is in exactly the same orientation as this, and this is in exactly the same orientation as this. And so it makes it actually pretty easy to get a channeling pattern. We certainly get an interference from the various structures on there, but we can get the pattern really without any difficulty. And looking at that, this is what they had looked at with their optical emission microscopy. This is now in one of these areas here where we see exactly the same sorts of structures, obviously much better resolution. We did some tilting experiments and we were able to get some of the dislocations to go out of contrast, which helps confirm to us that these really are dislocations. We didn't do a full analysis, but it certainly appeared that these are 16211 type partial stacking faults that are lying in the plane of these structures. And so we could look at it pretty easily. Okay, so just as a summary, and then I don't know if I'll do the last thing or not. Some folks here might be interested in it. Okay, sample preparation is certainly a lot easier for ECI than it is for TEM. That should be a thin foil, not a thing foil. only had that up there for a couple years. Okay. It only requires us to prepare one surface. It can be non-destructive. I can actually look at it and see if I have dislocations, then do the deformation and see how the dislocations actually appear. And so that makes it quite useful for us. We can look at very large areas. You know, with a fib, you can do some very nice site-selective TEM foil preparation these days. But you still have to take samples from a lot of different places. Here, I can look all over the place without actually damaging the sample. So there's some advantages there. So this makes it very conducive to in-situ experiments. We have bulk samples, more representative in terms of their state of stress. We have a large SCM chamber, so it gives us a lot of options. We can actually now do this at, we haven't imaged dislocations yet, but we can certainly do in-situ experiments up to 900 degrees C with straining. So we can do lots of different things there. Certainly, it's going to be less prone to sample preparation artifacts. It maybe won't eliminate them. We still have to prepare a surface. We still have issues with image forces on dislocations. But we can track those a little bit better. And we can look at very specific areas of interest where TEM, that historically has been more difficult to do. With a fib, you can perhaps do that a little bit easier now. But this gives us some real advantages. So just kind of in summary, this really summarizes the other things that I talked about. A couple of minutes? Okay. So what I'm going to do is I'm just going to jump ahead to something that, I don't know, maybe interests civil engineers a little bit more. Because technically, this is a school of civil engineering, isn't it? Okay. And so I got working with Ian Patterson when he was at Michigan State and Rachel Tomlinson. She was on sabbatical from Sheffield. And they're doing fatigue tests in compact tension specimens. And they have crack tips, and I said, oh, I can look at crack tips. Well, it turned out that their crack tips had a lot of dislocations, okay? And we couldn't really image them specifically. But what we ended up doing is we said, okay, what happens if we look at this whole area out in front of crack tip? And so this is very large. I mean, compared to what we would typically look at with the things I do, this is a huge area. But they're very interested in what is the size of the plastic field here. And that is something that historically has been very difficult to do. They're using thermal imaging during fatigue to actually measure that. They wanted to know if they were right. I said, well, maybe we're right. Okay? So what we do is we collect a whole bunch of backscattered images there. And that's really simple to do. Just go in there, have an undergraduate snap image after image. But what happens is the images near the crack tip look different than the images far away. Because near the crack tip, there's more dislocations, there's more crystal rotations, and the channeling contrast is going to be different in those areas. So as a consequence, again, if you move far away, you can see the grain structure in these backscattered images fairly easily. But close to the crack tip, because of the crystal rotations, we get more channeling bands and things like that. It becomes harder to see those. And what we said is, if there's a change in this contrast like this, maybe what we can do is do a Fourier transform on that. And when we did that, it was very, whoops, sorry about that. It was very clear that the Fourier transform changed because the frequencies in the images were changing. And again, these are fairly low magnification images. That's 100 microns there. And if we take a trace across those, we can actually turn around and measure the full width at half peak. We do a bit of cleaning up to do that, and which now gives us something that says, okay, the full width at half max is going to change as we deform the material. So can we quantify that? Well, to quantify that, we did an in-situ straining test of the exact same material, and we measured the full width at half max on a large number of images over these different strains. And so we developed really what's just a calibration curve. Here's the full width at half max for various engineering strains. And by doing that, then, we were able to take this crack tip area, and again, here's 1 millimeter, and actually map out what is the strain in front of the crack tip. Now, you know, I'm a microscopist, and everyone keeps working smaller and smaller, okay? But this is macroscopic. This is actually fairly easy to do. And, you know, like I said, I think maybe civil engineers appreciate this. When I show this to mechanical engineers, they get really excited because this is the scale they're interested in. And it was kind of amazing. As far as we could tell, no one had ever taken this kind of approach before. We recently published it in the Proceedings of the Royal Society, so they must have liked it. And we were able to go back and then make a comparison with the von Mises, the Dugdale, and the Irwin plastic zones. And we can see that, you know, it's actually pretty consistent. And so I thought I'd throw this in as something that maybe a few folks around here might be interested in. It's really exactly the same approaches as we're taking on the microscopic level, really at a much more mesoscopic level. So I think that's your slide. Okay?
Thank you very much. I'm afraid today is a hard day for him. I have to take him to class. So you have...
I have 2.5 hours of lecture today.
Yeah, that's it. We work a lot here in Spain, I promise you.
Every day, I know. Siesta, right?
After that.
Okay.
Yeah, so we have time just for 2 very easy questions. Well, we have one there.
Thank you very much for the presentation. It's very nice. Thank you all these nice pictures. I think it's going to really help to improve our knowledge, especially the fractal mechanism. I'm looking at this study, and
I hope.
when you are rocking the sample here, I mean, you're rocking the sample.
I'm rocking the beam. Yeah.
So you need special arrangements, or you can be like easily used with one facet microscope like the one we use.
Okay, it depends. It used to be a lot of microscopes offered it standard, okay? Because you can use your scan coils to rock the beam if you change the strength of some of your other lenses. But typically that rocks at a large working distances. The Joel 840 series would rock at 40 millimeters, and then there's other problems with that. Okay? So our microscope, we have 2 microscopes that can do this, actually have a dedicated set of rocking coils, which makes life easier. And so a lot of people ask me, could I do this instead of with secondary channeling, can I do it with EBSD? And my answer is maybe, okay? You know Stefan Zephyr at Max Planck in Düsseldorf? Okay, he's an EBSD guru, and he has a program that allows him to get an orientation with EBSD and then predict what tilts you need to get to what various channeling conditions. Okay. The problem is if the EBSD pattern is only accurate to about 1 degree, that is going to cause some problems. But what they do is they get close and then they adjust the tilt slightly until they get nice contrast. And so I think it works fairly well. The other thing that I've thought about, and we may do this because we want to do some things in our dual beam fib which doesn't have this, okay, is if you co-mounted a piece of silicon to do your orientation calibration and then got a channeling pattern at low magnification, which you can do in any microscope on that silicon, you could calibrate the relative positions between non-tilted and tilted, which would help you with that accuracy.
One more question.
Yeah? Better than TEM, okay. What we're doing, and I talked about this a little bit yesterday, we're doing some 3D X-ray at argon, okay, which allows us to get a 3-dimensional orientations, okay, which helps us. But we also, you know, these are Lowy patterns that we get. And Lowy patterns streak from dislocations. And if you assume the dislocations are edge dislocations, you can determine what the streak direction should be. It's not as clear if they're not edge dislocations. The person who does this, Rosa Barabash, she says, oh, don't worry about screw dislocations. I worry about screw dislocations, okay? But at least in every case that we've looked at, and we've looked at about a half dozen, from the dislocations that we've characterized based on trace analysis, the streaking we get in 3D X-ray is consistent with that. So is it perfect? No. Are there surface relaxations? Yes. It's moving us forward, okay? What we're doing, and I talked about this some yesterday, is we're taking, we're deforming some various microstructural packages. We map them with EBSD. we do a little bit of 3D, and then we're turning around, we're simulating those with the guys at Max Planck using crystal plasticity. And, you know, from a general sense, they match up pretty well. Where we get in trouble there is the details at grain boundaries. Because the CPFM, FEM doesn't handle grain boundaries very well. But it may also be that we've got problems with our experiments because I don't know what the inclination of a boundary is. You know, that geometric factor I gave is only based on this orientation. It doesn't say anything about the boundary orientation. So, you know, these are hard problems. And maybe we're making a little bit of progress on them. But we've got a long ways to go, which is good because I want to keep working for the next few years. Yeah. Okay. Off to class, right? Right.